All right, so this video is going to be on the chain rule. And we're going to have two different videos on the chain rule. We're going to have this one, and then we're going to have one that's more focused on trig functions. So if you want to put chain rule part 1 or whatever, that would be fine. So the chain rule is used when we have composition of functions. So what that means is that when you look at the function, you should be able to see some part where there's something inside and something outside. So I'm going to write to myself inside and outside functions. So this is different than multiplying functions, which was the product rule, or dividing functions, which was the quotient rule, or adding and subtracting them, which was sum and difference. This is saying now we're looking at a function that's kind of inside of another one. And you guys have seen problems like this. You've even asked me, and up until this point, the only way we had to do those problems was using the limit definition of the derivative. So now we're going to have a new method. So we're going to say, if you start off, actually, I'm just not going to put this as a bullet. If you start off saying that your function is capital F of x, and that that function is based off of a composition where you have a function where g of x is being plugged inside, then the derivative of this composition is going to be the derivative of the outside function with whatever was inside it, still inside it, looking all normal, multiplied by the derivative of the inside function. Okay, so we're going to say deriv of the outside, inside stays the same, multiplied by the derivative of the inside. That's what the formula is. All right, so we're going to do some examples, and the instruction for all the examples is just going to say differentiate. It's commanding you. Differentiate. Okay, so the first one is y equals x squared plus 1 to the 100th power. So we're going to rewrite this. We're going to say y equals, and if I'm looking at this composition and I want to see what's composed, then I'm going to say this is the inside function raised to 100 as an exponent. So that's our inside function, all right? So that means that if we're talking about this, then our f of x function is x to the 100th, and our g of x function, our function that is inside, is x squared plus 1, right? So that's saying we're going to take the derivative of the outside function, and we're going to leave the inside function inside of it, and then we're going to multiply by the derivative of the inside function. Okay? So if we look at this, for my derivative, I know that anytime I take the derivative of something like this, I take the exponent, I drop it to the front. So I'm going to take the 100, drop it to the front. And then I take that exponent and I subtract 1 from it. So 100 minus 1 is 99. So I just did the part where I have the derivative of the outside function and the inside function is just sitting inside. I haven't done anything with it yet. Now I need to take that and multiply it by the derivative of the inside function. If I'm looking at x squared plus 1, the derivative of that is going to be 2x. So I'm just multiplying this by 2x. So overall, I'm going to say my derivative is 200x times x squared plus 1 to the 99th power. All right, for the second one, we're going to have y equals the square root of 3x squared plus 5x minus 2. So again, we can think of this one as an inside function and an outside function. So I'm going to say this is like taking the square root of whatever the inside function is. So we would say our outside function is the square root of x, and the thing that we plugged in that was 3x squared plus 5x minus 2. So we've got our inside function, we've got our outside function. So we still don't know a lot about dealing with square roots. That doesn't fit any of our rules, the constant rule, the constant multiple rule, the multiple, what, all those rules we had. It doesn't really fit that. So I'm going to go ahead and rewrite this original problem as 3x squared plus 5x minus 2 to the 1/2 power, because once I have an exponent up there, I know how to handle that. And now I can go ahead and look for my derivative. So I'm going to take the exponent, bring it to the front. I'm keeping the inside function the same because I'm just dealing with the outside right now. And then I take this exponent and I subtract 1 from it, so that gives me negative 1/2. After I've taken the derivative of the outside function, which is what I just did, now I can multiply by the derivative of the inside function. And this inside function has two things I'm going to find the derivative of, so I'm going to put those in parentheses. So I've got 6x plus 5. All right. So we could say this is the final answer. A lot of mathematicians would probably not necessarily leave the answer looking like this. So this parenthesis right here has a negative exponent. That tells me that it could be, and in this case we're going to do it, could be on the bottom of the fraction. I know that I've got the fraction 1/2, so I'm going to go ahead and put the 1 on top and the 2 on bottom. This was negative, so I'm going to put it on the bottom. And since it's a 1/2, I know it's a square root, so I'm going to go ahead and put it down there as a square root since that matches the form of the original problem. And that's going to give me 3x squared plus 5x minus 2 that was underneath that square root sign. And then the 6x plus 5, it does not have an exponent, but if it did, it would be a 1. That's why we don't have to write it. And so I can just put that on the top. 6x plus 5 on the top. Now technically we don't need that 1. You can leave it there, you can erase it, it's up to you. But that's what our derivative is. That's an alternate form of the same thing. Now I will say, I think it's good practice to be able to take it and transition and write it this way. So I'm going to say I wouldn't necessarily mark you down on a test for writing it this way, but this is always my preference. So it's a good habit to get into. I just want to make sure you guys know how to fix those if you need to. Okay, one last example. So we're going to say we've got f of x, and I'm not going to use f of x. Well, we'll call it h of x. Since we were using f of x and g of x for our inside and outside functions, I don't want to confuse you. So we're going to say the function is 1/x squared plus x to the 4th, and this would normally be a quotient rule problem, but we can actually do this problem using what we know about inside functions and outside functions, because we can say that this problem is h of x equals 1 divided by I, 1 divided by the inside function. So that would mean that your outside function was 1/x, right? 1/x, and that would mean your inside function was x squared plus x to the 4th. So it is possible to do this without using the quotient rule. Now, if you recall, 1/x, most of us, hopefully, would not have left that as 1/x because that would still be a quotient rule. You can rewrite this as x to the negative 1 power. So that's what we're going to do. We're going to take our original function, and we're just going to say, since that's a 1 on the top, that's the reason this works, we're going to write this as x squared plus x to the 4th to the negative 1 power. So that's the same as having the entire thing move to the bottom of the fraction. So now I can go ahead and find my derivative. So I'm going to take that exponent, move it to the front, so negative 1, and I've got x squared plus x to the 4th. My exponent subtracts 1, so now it's at the negative 2 power. So I've done the derivative of my outside function. Now I have to do the derivative of my inside function, and I get 2x plus 4x to the 3rd. So again, if I want to go ahead and rewrite this, thinking of my negative exponents being on the bottom and my positive exponents being on the top, now I can keep the negative 1 on the top where it was, and on the bottom I'm going to put x squared plus x to the 4th squared. And that fits what we know about quotient rule, right, where the bottom ends up being squared at the end. So that fits that. On the top, this is an exponent of 1 and it's positive, so all this stuff would go to the top. And most math people would take that 1 and distribute it to the top. So I'm going to say to have my final answer in the way that is a little bit more traditionally stated, this is what I would have. Although technically I guess you'd switch those orders, but close enough.